So now let's continue chapter 2. So chapter 2, we start with the last part, thermodynamic models. So we explained what is meant by heat capacity. We have two types of heat capacity at constant pressure, heat capacity at constant volume. At constant pressure, we are using to calculate enthalpy. At constant volume, we are using to calculate internal energy. Then for liquids, for solids, Cp and Cv are the same. Any change in internal energy equal any change in enthalpy. But for ideal gases, Cp equals Cv plus R. So we have a change in internal energy different from changes for enthalpy for ideal gases. Also for ideal gases, we explained the ideal gas equation of the state, PV equal nRT. We solved some example using this equation, and today we will start with this example. Okay, so this example says we need to use the ideal gas law. We need to calculate the specific volume. So again, here, the specific volume. So this is the V hat. So this means volume divided by mass. This is the specific volume. We need to calculate specific volume of steam in liter per kilogram at each of the following temperatures and pressures and compare it with the steam table. We have 4 conditions, 4 temperatures, 4 pressures. We need to calculate the specific volume at each one of them. Again, these are the values of R that we can have or we can use in this one. Okay, so we have R in units joule per mole Kelvin. We have value of R for atmosphere, feet cube per pound, molar and kind. We have R for bar, centimeter cube, mole Kelvin, and we have R for PSI, feet cube per mole Kelvin. So we have these values. We have other values, by the way. We have one more value. Let me write this one. We have another value of R, which is 0.08314 liter bar per mole Kelvin. It's derived from this one. So, but this is another value that we can use. So all of these are value that you can use here. Okay, let's try solve this one, and then let's see what the steps you can do in this one. Okay, so let's see what we have. Let's start solving the first one. So again, here in this example, we have ideal gas law. So ideal gas law, we know that it's PV equal nRT. Always keep in mind what you need to calculate. I need to calculate the specific volume. Specific volume is volume divided by mass. In the equation I don't have mass. But I know that this N can be related to mass. So this N is mass divided by molecular weight. So the equation I have, so this one will be PV equal mass over molecular weight RT. If we divide both sides by mass, then I have PV over mass. This will be RT over molecular weight. Now you can see that I have here in this term volume divided by mass. This is the specific volume I need to find. So the equation here I have, this one will be pressure times specific volume equal RT divided by molecular weight. Or in other words, the specific volume, the property that I need to calculate, this one is RT over pressure molecular weight. Start to put the conditions you have in the problem. So we have the temperature. Let's start with A. We have temperature is 100 degrees Celsius. We don't use Celsius, we use Kelvin. So this one will be 100 plus 273. So this one will be 373 Kelvin. Then we have the pressure is 0.1 bar. I can keep it 0.1 bar. I keep bar. I can convert it to Pascal. This is fine. So based on the pressure units, This will be the value of R you will select. So now we can use R value, this one, 0.08314 liter bar per mole Kelvin. And why I select this one? Because basically here I have this one is bar and I have the pressure is bar, so I don't need to convert the pressure. Also, I need the specific volume to be in liter and this one here in liter. So it will give you part of the solution I have. So molecular weight of H2O, so it will be 2. The atomic weight of hydrogen is 1 plus atomic weight of oxygen is 16, so this one will be 18. This will be given. There is no need to do this calculation. The atomic molecular weight is given. So we have everything, so substitute in the equation the specific volume equation, and you can calculate the specific volume, and this one will be 17.221. This is a specific volume per mass. What will be the units of volume? Liter, because the volume units in the R value is liter. So this one will be liter. But we have no idea this will be liter per gram or liter per kilogram. Can be any one of them, right? So which one of them will we have? Liter per gram or liter per kilogram? Remember that we need to calculate in liter per kilogram. So if this one is liter per kilogram, this is what we need. If it's liter per gram, then we need to modify it. So what do you think? Liter per gram or kilogram?
Gram.
Gram. Why?
Because the molecular weight is grams per mole.
Nope.
No? Oh.
The molecular weight is gram per mole, kilogram per kilomole, pound mass per pound mole. This is why we don't put the units.
The R constant is per mole.
Yes, R constants. The R is per mole. Mole is equivalent to gram. So this is why here we have this one, it will be liter per gram. Okay, this is not what we need. We need the number to be liter per kilogram. So this is the units we have, not this one. Then the specific volume we have will be 17.221 times 10 to the power 3. So this will be 17.221 liter per kilogram. And this is what I need to calculate. Is it clear? So usually the common mistakes we have here, the value of R that we are using, that missing this conversion at the last step, just put the number, this is what we need. So always make sure to check the units you have. Check that are given in the example, the units that are required from you to represent the numbers in it. Clear? Any questions? You can repeat the same steps for the other requirements, B, C, DE, and if you do all of this, so this will be the value we have. So this is the value of the specific volume for requirement A. This is the conditions at requirement B. These are the conditions C. These are the conditions D. So these are all the answers we have for the problems. The second part is to compare these results with the results we have from the steam tables. So if you get this temperature and pressure, go to the steam tables or the Excel file that you have, you can just put these conditions. This will be the values of the steam tables. So now if we just compare it, at 0.1 bar, the difference between the specific volume you calculated from the ideal gas equation and the specific volume you can get from the steam tables is very small. So the values are almost the same. At 1 bar, the difference between your calculation and the value of the steam table is still less than 1%. At 10 bar, the difference is 60%, which is still acceptable. We have a small error. But at 50 bar, at high pressure, you have a large deviation here. So the thing here, we can see that at low pressure, ideal gas equation of the state, which is PV equal RT, can give accurate results. And here roughly we can say for pressure values less than or equal to 10 bar. But if the value of the pressure is more than 10 bar, then we have large errors in ideal gas equation of the state predictions. This is clear? Question?
Yeah, I just wanted to ask, I don't know if you mentioned this earlier, but do we need to know the R values? or
No,
they can
this,
be given?
it will be given. All the R values will be given.
Gotcha.
Okay? Just you need to pick which one you select. Clear? So now, if you have problem, and this problem at low pressure, you can use ideal gas equation of the state. This is fine. But if you have high pressure, then you have a problem in using this equation. And why we have this deviation happen? Because if you remember, when said if you have ideal gas, so we are assuming that the volume of the molecules can be neglected. You are assuming that the intermolecular forces also can be neglected. Okay? So if this is the ideal gas equation of the state, so it's missing these two like considerations. Molecules volume, interaction between the molecules. So this is why we need to update this equation to account for these two changes. So the first one, or the first update we have, we can correct the ideal gas equation of the state by adding this parameter V, and this parameter V account for the volume of the molecules. So now the volume of the molecules cannot be neglected, especially at high pressure value. Because at high pressure, the space volume will be small, so the volume of the molecules cannot be neglected compared to the total volume of the gas. So we can add this parameter B. This parameter we need to add to the equation to account for the volume of the molecules. Also, we need to add another parameter accounting for the interactions between the molecules, and this parameter will be A. And now we can modify the ideal gas equation of the state from this formula to this formula. Okay, and the one who did this is van der Waal. So this is why the equation here we have, this is what is called van der Waal equation of the state. And basically, if you have van der Waal equation of the state and you put the value of A as 0, so this term will be cancelled. If you put the value of B, so now you are cancelling the intermolecular forces. If you put B as 0, so you are cancelling the molecular volume, so you will end up with the ideal gas equation of the state. Okay. Just two parameters, A and B. Each one of them represents like one of the considerations that the ideal gas law is missing or assuming to be neglected, and we are updating the equation we have. Okay, so this is the ideal gas equation of the state, and this is the general representation of, this is the van der Waal equation of the state, and this is the representation of it. So van der Waal in 1873, he proposed this equation, and he said, we have this equation overcome the limitations of the ideal gas equation of the state, and this equation we can use at high pressures. So now at low pressures, we have simplified ideal gas equation we can use. At high pressure, we have van der Waal equation of the state also we can use. What are these parameters? So as we said, A and B, these are positive constants. These positive constants represent molecular volume, interaction between the molecules. We have equation to calculate each one of them. Again, there is no need to memorize this equation. All of this will be given. You can calculate A from this equation. You can calculate B from this equation. Just you can see this equation contains R, the ideal gas constant, contains critical temperature, critical pressure, and critical temperature and critical pressure. If you remember when we showed the appendix in the previous lecture, we can get the values of these critical from appendix C. Okay, so you have these values from the appendix. Okay, and again, if you just put A and B as 0, then you will return back to the ideal gas equation of the state. So far as clear? Okay, van der Waal said we can use this form to calculate or substitute in this form to find any parameter or any property you have, or you can, like he put another formatting of this equation. He can say also the ideal gas equation of the state can be represented in terms of something called compressibility factor, Z. And you can say Z equal all of these things. Again, this equation contain A, contain B, the van der Waal parameters we have. This is again van der Waal equation of a state, just another way of representing it. So we have two ways to represent van der Waal equation of a state. They will give the same results. One in terms of compressibility factor Z, another one without this compressibility factor Z. So the question, what is Z? What is this compressibility factor? Z compressibility factor, this is just a ratio here we have that we can judge the accuracy of your ideal gas assumption. So we know that for ideal gas we have PV equal RT. Okay, so if we derive this equation for ideal gas, we can have PV equal RT is equivalent to 1. So instead of 1, we put Z. So this D represents compressibility factor. So if you have any equation, just calculate PV equal RT, calculate Z. If the value of Z is close to 1, then this means the ideal gas equation is valid to be used in this in your problem. If the value of Z is far away from 1, like 0.4, 0.3, so this means the ideal gas equation of a state cannot be used in your problem. So again, compressibility factor Z, this is one of the methods we can use to see, can I use the ideal gas equation of a state or no? So basically, calculate Z, and Z is PV equal RT. If the value is Z is 1, 0.95, 0.9, so this means the behavior of this gas can be assumed as an ideal gas, and you can use ideal gas equation of a state. But it's far away from 1, then you cannot use this equation. Similar to, as I said, at low pressure, use ideal gas. At high pressure, use van der Waal equation of a state. So just if you need numbers, calculate Z. If Z close to 1, use ideal gas. If Z away from 1, so don't use the ideal gas. Clear? Okay. We have one of the important parameters. If you remember, we have critical temperature, we have critical pressure, we have critical compressibility factor. The value of the compressibility factor for this or for any gas at critical temperature, critical pressure, and its value is constant, 0.375. We will use this number in the equations we have in chapter 7. Okay? So far is clear? Any questions? Okay. So let's see if we have this example. So this example, it says we have H2O. The following parameters have been proposed for the van der Waal equation of the state. A, we have the value of A given. We have the value of B given. Find the specific volume. Again, specific volume is volume divided by mass. Find the specific volume at the temperatures and the pressure we have in this example. Okay, so how we can solve this problem? So the easiest thing, we have the van der Waal equation of a state. So we have so it says we have P is RT V minus B minus A over V square. Okay. So if we see the problems, so let's see requirement A. Requirement A, we have the temperature is 100 degrees Celsius. Again, we don't use Celsius. So this one plus 273, this will be 373 Kelvin. We have pressure, 0.1 bar. We can leave it as bar. Then we have R, this one is 0.08314 liter bar per mole Kelvin. So this is the value of R. The value of A is given. So the value of A is 0.5542 Pascal meter to the power 6 divided by mole square. The value of B is 3.051 times 10 to the power negative 5 meter cube per mole. So we have all the value, substitute all of this number here. So substitute in the equation. And then you can find the value of molar volume. But again, the requirement is specific volume. So what you need to do, just divide by the molecular weight in order to make this conversion. Okay? So if you put the numbers in this problem here, this will be the values you have. So for the first conditions, A, this will be the value of the specific volume in liter per kilogram. If you substitute with requirement B, we have this one. If you have C, if you have D, so you can find the problems you have. Just direct substitution in the equation. Clear? Okay. The last part that we need to have, we have an example. So this example, we have 110 pounds, which is equivalent to almost 50 kilogram of liquefied natural gas, LNG, is stored in a rigid sealed vessel with volume 5 feet cube, 0.14 meter cube. Due to a failure in the cooling insulation system, temperature pressure increased to negative 100 Fahrenheit, which is above the critical pressure. Thus, the natural gas will no longer be in the liquid phase. So the clear here, when we have natural gas and we need to transport this natural gas, it's easier to change its phase from the gas to liquid and transport it or export it as in the liquid phase. So this is why it's called liquefied natural gas. But liquefied natural gas, to maintain it as liquid, you need like severe cooling conditions. You need very low pressures, you need very low temperatures. If you can see this example here, negative 100 Fahrenheit, this is considered a high temperature for the liquefied natural gas. Liquefied natural gas should kept at temperatures below these values, okay? Because at this condition, which is, it's 200 Kelvin, which is negative 73 Celsius, right? At negative 73 Celsius, this is a very high temperature for the liquefied natural gas. So the temperature should be below all of these values. So here he said, we have failure happen in the cooling system, so the temperature increase. Temperature increase, it becomes almost 200 Kelvin, negative 73 Celsius. We have, here it's required to calculate the resulting pressure. So as a result of this temperature increase, the pressure will increase. So we need to find this like resulting pressure. Here we have this vessel is safe if the pressure increase up to 500 atmosphere. If the pressure value increase, okay, at any value below 500 atmosphere, this is like a safe condition. Just to imagine this number, the pump is almost 10 atmosphere. So this time is 50 times any pump we have, okay? So if the pressure is below 500 atmosphere, so we have control system, efficient control system for this tank. So we still like have a safe operation. But if the pressure is more than 500 atmosphere, this pressure will rupture, okay? So here he's telling you that make your calculations, just make sure that you have safe operation or you have like a safety issue coming from this temperature and the pressure increase. And here he tell you, make the calculations twice. One time using the ideal gas, one time using the van der Waals equation of state. And if you will use the van der Waals, this is the value of A, this is the value of B. Just a simple calculation. Calculate the pressure and let's see what will be the resulting pressure. Compare this pressure to 500 atmosphere. If it's below 500 atmosphere, we are safe. There is no action that you need to take. If the resulting pressure more than 500 atmosphere, then we may have failure in the system. Clear? So let's start doing the calculation for this one. If we start with the first part using ideal gas, equation of state, which is PV equal nRT. In the example, we don't have N, we have mass. So we can say PV equal mass over molecular weights RT. The pressure, this is what I need to calculate. So start to put the numbers we have. The temperature is negative 100 Fahrenheit. We don't use Fahrenheit, we use Rankine. So convert Fahrenheit to Rankine, so this will be 359.6 Rankine. The volume is given 5 feet cube. The mass we have is 110 pound mass. Molecular weight, it's methane, CH4, 16 plus 4, 12 plus 4, so this will be 16. The value of R that you will use to be consistent with all of these set of units is 10.73 psi feet cube per pound mole Rankine. Substitute in the equation, calculate the pressure. So the pressure, the resulting pressure, this will be 5,306 psi, which is equivalent to 361 atmosphere. So again, so this one less than 500 atmosphere. So you can conclude that we have safe operation. And this is the first requirement. Everything is under control, we have safe operation. So if you use this ideal gas, so everything will be fine. If you repeat the calculations, but using the van der Waals equation of the state, so we have pressure is RT over V minus B minus A over V squared. So again, you have the value of R, temperature is given, molar volume you can calculate, volume divided by number of moles, you have the value of A, you have the value of B. Just note that the molar volume, this is volume divided by number of moles. We don't have number of moles, but we know that number of moles is mass divided by molecular weight. So this is how you can calculate the molar volume. Okay, we have molecular weight, we have volume, you have mass, so you can substitute in the equation. And if you did this, you will find the value of pressure as, let's put it here, 75,222 psi, which is more than 500 atmosphere. So we have not safe operation. So you see the differences we have here. You have a process and you have an issue happen to this process, and you as an engineer, you need to take action. So how you can take this action? Just calculate the pressure value. Based on the pressure calculation, you can know that your operation, your process is safe or non-safe. Okay. Again, you can use two equations that we have shown right now. One of them, it tells you everything is safe. There's no action required from you. But the other one tells you have an issue. You need to take action because the pressure is more than the failure pressure that the unit can withstand. So which one you will rely on? Which is van der Waals. Because we know that ideal gas equation of a state is valid at low pressure, right? But van der Waals, this one is supposed to be accurate at high pressure. But here in this one, the ideal gas, this is the most accurate one, even if you have high pressure value. So there is something missing here. So how come van der Waals proposed an equation to overcome some of the limitations of the ideal gas, which is very accurate at low pressure? So the equation that it's supposed to work very accurately at high pressure, it fails. The equation that's supposed to do poor calculations at high pressure, it gives very accurate conditions at these very high pressure. Okay, so we have still something missing in explaining both equations that we have. Let's start with the van der Waals. Van der Waals equation of a state, why it fails in this problem? This because of the definition of parameter A and parameter B. So van der Waals said we have parameter A accounts of the volume of the molecules. Parameter B accounts for the interaction that happens between the molecules. But van der Waals, he assumed that A and B values are constant. And this was the problem we have here. Because with changing the pressures, the molecules will be closer, then the interactions will increase. Van der Waals didn't capture this thing. So he assumed that regardless the position of the molecules, always molecules will have the same interactions at all temperatures, at all pressures. If you remember A and B equation, it wasn't depend on the pressure or temperature. It depended on the critical temperature and critical pressure, and these are constants. So this is the issue that we have with van der Waals equation. Van der Waals equation, he assumed that A and B are constants. So this one, or this was the problem that A and B were not very effective at this extremely high pressure. But on the other side, we know that the ideal gas law is only valid at low pressure. So how come at this high pressure, okay, the ideal gas law becomes very valid? Do you remember Z, compressibility factor? We said you need to calculate Z, right? If Z close to 1, then the ideal gas equation becomes valid. So basically here at this value, here we have this relation Z on the y-axis, pressure on the x-axis, to 4 pressures like less than 5 megapascal. So the value of Z is close to 1. Right? So this means within this range, we can use ideal gas equation of state. If pressure increase, what is happening to the value of Z? It deviates from 1, becomes far away from 1. Then we can't use. But then what is happening? After like 10 megapascal, the value of Z start to increase again. Okay, when it start to increase, so the value of Z start to increase, and at some conditions, so what is happening to the value of Z? It becomes again 1. So we have here a range at extremely high pressure. At this condition, the value of Z is closer to 1. So even if there's an extremely high pressure, but the compressibility factor is close to 1, so you still can use the ideal gas equation of state. This was the case of the problem we have. So the problem we have, we are making the calculations within this region, so this is why the ideal gas gives you like accurate results. But the van der Waals, because he assumed that A and B are constant, he doesn't account for this pressure variation, so the van der Waals calculations fail in this one. So again, van der Waals failed because there is no single value of A and B can fit for all the conditions we have. So far is clear? So again, so far we have ideal gas equation of state valid at low pressure and at extremely high pressure. Okay, van der Waals equation of state, it's valid at high pressure but not very extremely high pressure. Okay, so do you think these are the only equations we have? No. The tip here that van der Waals equation of state, this is very advanced equation. It was considered a breakthrough when van der Waals developed this equation. But we still use, or nowadays no one is using it, by the way. In the exam we can use it because mathematically it's simple. So we can make calculations in the exam using van der Waals equation of state. But in real life, in simulation packages, for example, when they need to use an equation of state, actually they did use van der Waals. They are using like more accurate, more complex equations. Okay, these equations developed based on van der Waals, replacing van der Waals equation of state, and all of these equations discovered in chapter 7. Clear? So this is why next lecture we will start chapter 7, not 3. We need to complete the same like scenario. What are the other equations of a state we have that completes or overcome the issues we have with using van der Waals? Okay. See you next lecture.